Welcome to Session 1 of the Intro to GameTank Programming tutorial series. Previously, in Session 0, we went over how to set up your development environment. In other words, installing the tools needed to compile and test code. In this session, we'll cover the basics of 6502 assembly programming, and draw some simple graphics. We'll learn about registers, branching, and interrupts as applied to game programming. So, what exactly is assembly? If you've heard of assembly before, you may have heard that it is difficult, old-fashioned, or just really tedious. However, by learning only a few simple principles, it can become a handy tool for making games that run smoothly. Imagine the computer as a video game protagonist. It has a few different moves that can be used together to accomplish a wide variety of goals. In order to use these moves, a player must communicate their intentions through a series of button presses. You, the programmer, play the role of a strategy guide author in this metaphor. You write a description of what the game protagonist should be doing, and the player's job is to convert the description into button presses. This scenario is analogous to how modern programming languages are used, where the button presses represent the machine language code stored in program files. Suppose that, for a particularly delicate section of the game, you needed to tell the player an exact series of commands, rather than leaving it up to interpretation. Instead of saying just the button labels A, B, Start, you might use names of immediate actions they trigger, Jump, Punch, Pause, for the sake of readability. Essentially, that's just what assembly language is. Raw machine language data is not particularly human-readable by itself. By using shorthand commands written in English letters, a human can fluently program a computer down to a cycle-by-cycle granularity. Luckily, the 6502 CPU we'll be using has a comparatively small and easy-to-remember collection of commands. While the modern AMD 64 instruction set has over 900 unique mnemonics, the 6502 has 56. Don't worry if this still looks like a lot. Many of these are simply variants of the same general function. LDA, LDX, and LDY, for instance, all do the same thing, load a value, but place the result in different locations. Before long, you'll be familiar with the different moves available to you, and these abbreviations will become second nature. Now, let's finally start writing some code. We'll create a new folder in our repos folder and call it Hello GameTank. Inside the GameTank emulator repo, look for asm/tutorial/blanktemplate.asm. Copy this into your new Hello GameTank folder and name it hello.asm. This file gives us almost the simplest possible starting point. The only line of code that runs is jump forever. Jump, short for jump, is an instruction to move to another part of the program and start executing code there. Forever is a programmer-defined label. Anywhere you see some text without a space, ending with the colon character, that denotes a label. Reset, IRQ, and NMI are also labels. When a label is provided as the target of an assembly instruction, it will be translated to the address of whatever comes after that label. So in this case, forever will be translated to the address of the jump forever line itself. In other words, jump forever is an infinite loop. Now, at the very top and bottom of the file, we have some lines that aren't actually assembly instructions. Since they start with a dot, they are called dot directives, or .dirs for short. These features don't directly become machine code, as they are commands for the assembler rather than the CPU. .org, as in organize, tells the assembler that we want to start putting code at a specific address. This influences both the address values for labels and the production of our final binary ROM file. Here, we write .org hex E000, which is the starting location for an 8 kilobyte cartridge. The $, denotes a hexadecimal number, the decimal equivalent being 57,344. Personally, I find the hex version a little easier to remember. Down at the bottom, we have .org again, and then 3 lines starting with .dw. .dw, short for data word, can be given a number or a label, and is used to place raw data in the binary output. This section is .org at hexfffa. Any software project for a 6502-based platform will have something like this, which tells the CPU where to begin executing code after certain hardware signals are received. These pointers are called vectors, and in order they describe locations for the non-maskable interrupt, reset, and interrupt request handlers. Reset is used as the starting point for our programs. The GameTank will jump to this location when the yellow reset switch is pressed, or the R key is pressed in the emulator. Non-maskable interrupt and interrupt request, also known as NMI and IRQ respectively, are activated by system features that we'll cover later. They're called interrupts because they'll interrupt normal program execution to run immediately, and then return to whatever the program was doing before when they finish. For now, we'll place an RTI instruction after each of their labels. RTI stands for Return from Interrupt, so we're just making these interrupt handling routines do nothing and return immediately. Anyway, that's enough touring of a basically empty file. Let's add some code of our own. To keep up the thrilling pace we've had so far, we'll launch right into interacting with graphics hardware. Otherwise, it'll be hard to tell whether the program works or not in the emulator. Just after reset and before forever, we'll write instructions that will run just once. LDA #%01001101 STA DMA flags. I know, I've gone and dropped some arcane-looking binary numbers on you. LDA, or load A, is an instruction for loading a value into the A register, also known as the accumulator. The hash symbol indicates that we're using a value directly, as opposed to treating it as an address and retrieving a value from memory. The percent symbol denotes binary notation. The reason we're choosing this representation here instead of a nice non-threatening 77 is that we'll use this value to control a system setting where each binary digit is treated as a separate on-off switch. It would function the same way and generate the same machine code if we used decimal or hexadecimal notation here. But with a quick check of a reference to each digit's purpose, you can see at a glance which options are being toggled. From right to left, we have Enable the DMA Blitter Engine. Trigger an NMI event on every vsync. Enable Color Fill mode. Trigger an IRQ event when a draw operation completes. After we have loaded this value into the accumulator, STA, or Store A, is used to place it at the location labeled DMA flags. Since we haven't yet declared a label for DMA flags, though, it is meaningless and will cause an error when we try to compile. At the very top of the file, we'll give it a value. DMA flags equals hex 2007. This value is wired into the hardware design. On every cycle, the CPU emits a 16-bit address number on the motherboard. A set of logic gates, collectively referred to as an address decoder, activates a different chip to send or receive values based on that address. When hex 2007 is emitted, the register chip that controls certain video and blitter options is activated to receive values. While we're up here, we'll add a few more definitions for hardware addresses. Bank flags at hex 2005 mainly controls memory banking options, meaning that certain ranges of addresses can be mapped to different sections of memory. Add STZ store 0 bank flags just after reset to initialize this register to 0. Starting at hex 4000, DMA VX, VY, GX, GY, width, height, status, and color are registers that get a lot of use in a GameTank game. These are used to configure and launch a drawing operation that continues in the background while your program code may continue to run. It's important to note that these register addresses only apply when the Blitter engine is enabled. Otherwise, they map to video RAM. Let's try drawing a square now that we've created labels for the drawing registers. Many operations in assembly boil down to picking up a value, optionally doing something with it, and putting it back down. Load A #32, store A DMA VX, load A #24, store A DMA VY. We'll put the upper left corner of our drawing at x equals 32 and y equals 24. If you're storing the same value in multiple places, you can skip the extra pickup to save some cycles. Load A #8, store A DMA width, store A DMA height. We'll set both the width and height of our drawing to 8 pixels. Load A #hex23, store A DMA color. We'll set our square to a vibrant shade of blue. Finally, we want to initiate the draw operation by storing a value of 1 in DMA status. Load A #1, store A DMA status. At this point, we should be able to see something when we compile this code and run it in the emulator. Save and open a terminal if one isn't open, and make sure to cd into the Hello GameTank folder. We haven't made a makefile yet, so we'll call Vasm directly. Vasm 6502 old style -.dir -wdc02 -fbin -o hello.gtr hello.asm. .dir enables .directives. WDC02 tells the assembler we're using the modern version of the 6502 by Western Design Center. fbin outputs a binary ROM file. -o hello.gtr tells it the output file should be named hello.gtr, and hello.asm at the end to tell it the file we want to assemble. Hit enter, and after that's done, we'll run the emulator. /GameTank emulator /bin /windows_nt /GameTank emulator.exe hello.gtr. If everything went as planned, a blue square should be sitting there on the screen. It won't do a whole lot at the moment though, since our program draws it once at a hard-coded position and then enters an infinite loop. Let's modify our code to make the square move at a rate of 1 pixel per vsync. First, we'll move our drawing code inside the infinite loop. Cut and paste everything between load A32 and store A DMA status to just after the forever label and just before jump forever. Then add the instruction WAI twice. WAI is wait for interrupt. This is useful when you know that your program has nothing to do until the next NMI or IRQ event. We're using it twice here because there are 2 interrupts that we're waiting for. An IRQ event will fire 64 cycles after store A DMA status executes, because the blitter runs at 1 cycle per pixel and we're drawing 64 pixels. Afterward, an NMI event will fire. indicating the start of VSync. When enabled, NMI fires 60 times per second and indicates the start of a frame being sent to the television. To make the square move, we'll replace the hard-coded value 32 with another register. Delete load A 32 and change store A DMA VX to store X DMA VX. Besides the accumulator, the 6502 also has the X and Y registers available. You can think of these as extra hands for holding on to numbers. Just before jump forever, add the instruction in X. In X stands for increment X, increasing the value of the X register by 1, or rolling over to 0 if the current value is 255. Save, invoke VASM again, and then the emulator. Frustratingly, the square isn't moving. There's one more addition to make in the code. Right now, the program is getting stuck in the IRQ event following the draw because the signal is not being cleared. Under the IRQ label, just before RTI, add storeZ DMA status. This will turn off the event signal, much like turning off an alarm clock. To make sure this handler runs, also add CLI, clear interrupt disable, before the forever label. The instructions CLI and SEI can be used to disable and enable all IRQ handling, also referred to as masking. This is what the non-maskable part of NMI refers to, as that interrupt handler can't be blocked. If you compile again and run the emulator, now the box will sweep across the screen. Let's finish the session by adding a background to keep the square from smearing, and making the square bounce left and right to learn about branching. First, we'll copy the section that sets up the blue square drawing and adjust the parameters. The maximum size for a draw operation is 127 pixels in width and height. Values from 129 to 255 are treated as negative and are used for flipping an image. Then, store Z can be used to quickly set DMA VX and DMA VY to 0. Change the color value to hex FE for a contrasting dark gray. Then, another Y instruction between the two draws prevents the blue square settings from interfering with the gray background. While the blitter is drawing, modifying its registers will interfere with the drawing operation, so we'll pause the CPU until an interrupt happens. Changing these registers during drawing won't damage the hardware or anything, but at the time of this recording, the emulator isn't designed to present the behavior accurately. The blue square is moving a bit fast, so we'll add another Y to wait an additional frame between updates. There are better ways to move something slowly than to pause the whole program, but this will do for now. To move the square back and forth, we'll update the DMA VX assignment once again to use a value in RAM instead of the X register. Change store X back to store A. Above it, load A 0. Here, we're not using a hash symbol, so instead of populating the accumulator with 0, we're fetching the byte stored at address 0. Then, we'll perform some addition to update this value. The instructions needed for this are CLC and ADC. ADC stands for add with carry. If you've ever done addition on paper, you'll be familiar with the practice of carrying a digit to the next column. When add with carry is used, a carry switch is set if the result would be greater than 255. If the switch is already set, then an extra 1 is included in the sum. CLC stands for clear carry. We use this before performing addition to make sure a previous calculation doesn't interfere with the current one. So, we write CLC, then ADC 1. Again, 1 is a memory location. We'll use byte 0 to track the position of the square, and byte 1 to track the direction. Save the updated value with store A 0 and write it to DMA VX with store A DMA VX. Up in the initialization section, we'll set byte 0 to 0 and byte 1 to 1. The matching is coincidental, as we could have easily used other memory locations, such as 34 and 4097. At the bottom of the loop section, we don't need increment x anymore. Instead, we'll load byte 0 into the accumulator again, and then CMP, short for compare, hash 120. Given a value, compare sets a switch called the Z flag if the accumulator is equal to the provided value. Before we can make use of this, we need to add some more labels. Move square right, move square left. When we want to conditionally alter the flow of our program, that's called branching. The branching instructions will jump to a code label under certain conditions, different for each branching instruction. Now, we want to use BEQ, branch if equal, then move square left. If the Z flag is set when this instruction runs, which will happen if byte 0 equals 120, we'll jump to that label. To handle bouncing off the left side of the screen, we'll write a check for when byte 0 is equal to 0. Compare hash 0, branch if equal, move square right. Finally, we'll put a jump forever so that if neither condition is met, we'll restart the loop. Under the move square right and move square left labels, we still need to add actions. For move square right, we just want to set byte 1 to 1. So, load A hash 1, store A hex 1, and jump forever keeps us from running over into move square left. Inside move square left, we want to instead set byte 1 to 255, or hex FF. Because all of the registers are only 8 bits wide, this will cause the value to roll over and have the same effect as subtracting 1. Jump forever is already at the bottom here, so we don't need another one. One last time, for this session, save the file, run VASM, and then run the emulator. Bounce, 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 bounce. Next week, we'll learn to draw images from compressed data and read gamepad input to make our program interactive. In the meantime, I encourage you to mess around with this code and see what else you can make the square do.